This is where I left you off, I think, in the last video. I made very minor modifications. But just to do a quick recap here, um, this basically is trying to minimize the loss function versus weight. So the loss function is a function of weight, and we are trying to minimize that loss function by gradually changing the value of the weight by leveraging the gradient, which is one of the most important algorithms, if not the most important algorithms in deep learning. So we change the weight using this formula here. Um, Weight minus eta, which is the learning rate, times the derivative. And the loss function here is y minus y hat, which is w times x. X is known, it's an input variable. Y is the output variable. So again, during training, we have the input data and the output data, and we are trying to find the best fit um, curve or line in this case, because W times X is a line, and we're assuming that the bias is 0, just to simplify the math. So if we expand this function, this is what you get. Then you do the derivative for this function, this is what you get. And we apply this equation for the weight, and this is really what you get. Eventually, what's highlighted in yellow. Now, let's add the bias back in, just using the math instead of using also a three-dimensional diagram. So it's again, if you remember, I mentioned this concept which we are using for two-dimensional space to explain the gradient descent is applicable to multiple dimensions. Same thing. So we added the bias back in. So now the loss function is a function of the weight and the bias. And this is what you get. Feel free to pause the video and really try to internalize, rationalize what's happening here. And then we have to do the partial derivative because we have a function of more than one variable. So we do the partial derivative of the loss function with respect to weight. This is what we get. The partial derivative with respect to the bias. This is what you get. And what's highlighted in yellow eventually is the equation for the weight and the bias. And it's really interesting. This looks really similar to this. So if you look at the weight here and the weight equation here, it looks really, really similar, except now we have the bias added here. That's fascinating. This is elegant math. So we take all this information together now. Let's go through the process of doing the optimization or conversion on the weight and the bias to come up with the best fit line. So you must have seen this in one of the previous videos, but I kept it sort of at high level. We go into a little more details here. So we randomly select the value for the bias and the weight because we really don't know where to start. So we select randomly. We set the learning rate, eta, and we set the number of epochs. The epoch is basically an iteration that goes through all the training data one time. Going through it one time is one epoch, all the training data. So we get the next input-output pair. We calculate y hat. So we have all these values available. We have the weight, we have the input, we have the bias. We also have the actual output, y. So we calculate y hat. We calculate the loss, which is y minus y hat squared for this particular input-output pair. And then we just apply the equations that I shared with you on the previous slide for the weight and the bias. This actually gives us the next value for the weight and the next value for the bias that will take us closely to the minimum of the loss function. This is really the objective. We're trying to minimize the loss function. This way we identify the best fit line. Then we ask the question, are all the samples processed? Meaning each pair is one sample. Each input-output pair is one sample. Then we ask the question, are all the samples in the training data processed? If no, then we go and get the next pair. We keep doing this loop until we are done with all the samples. So we go through this process right here until we are done with all the samples. This is when we go through all the samples, this is one epoch, just one epoch. If we are done processing all the samples, then we ask another question. Are all epochs executed? Have we finished? Have we done all epochs? If the answer is no, then we store the loss, and this is important. You store the loss for each iteration or for each epoch, and then we start the next epoch. If all epochs are executed, so basically we went over all the samples, and then we went all over all the samples for all the epochs, then we have the final values for the weight and the bias, and this would be our best fit line or our best fit model for now, because it might not be the best. And then the next thing would happen is we go through validation and testing activities for this fit model that we got through this process, the training process. So I introduced the different types of gradient descent in one of the previous videos. I would like you to think about what type of gradient descent we are using in this particular process. I think it's important. And by the way, we typically, software engineers put a flow diagram such as this before we start programming. That's really the right way to do it, because you find yourself running into issues, and then to fix these issues at this level is much better than fixing the issues while you are in the code. So I hope you came up with the right answer for the gradient descent type that we are using in this process. And it's the stochastic gradient descent. So, couple observations about this flow. There are, of course, a number of different things that can be done to really optimize this flow. But couple observations. The number of epochs may be too large or too small. If the number of epochs is too large, we run the risk of the model overfitting the data. What this means is the model is so good on the training data. It describes the training data very well. But when you give it input data that it has not seen, it does not do very well. And this could be because the model was overfitting the training data. If the number of epochs is too small, optimization would be unlikely or less likely. And that also depends on the learning rate, which brings us to this other observation. If the learning rate may be too large or too small, if it's too large, optimization is unlikely. If you go back and look at the parabola and the learning rate is too large, you will be taking larger steps as you are changing the weight value. So it's very possible you could miss the minimum. Like you get closer, relatively speaking, to the minimum of the loss function, and then the next step you take, it takes you over the minimum because the step is too large. Now, if the learning rate is too small, then you take very little steps and you run out of number of, you exhaust the epochs, and the optimization would also be unlikely. You take very little steps and then you get close to the minimum, but you could do better, much better. You get closer to the minimum, but not very close. And so optimization is really unlikely. Optimization meaning you did not really minimize the loss function and you did not identify the right values for the weight and the bias.